Hello, everyone. My name is Donald Loveland, and I work in the Materials Science Division at Lawrence Livermore National Lab. There is no doubt that graph neural networks are becoming more prevalent in predictive modeling tasks. For us within the Materials Science Division, we often leverage graph neural networks to model the relationships between molecular structures and more macroscopic material properties. And as with many domains, once we have a model that works well, we are always interested in determining how the model is making decisions and how those decisions can be relayed back to domain experts. That said, with the current field of explainable AI providing a myriad of different methods to extract insights, as well as the multiple ways that we can extract insights from graph neural networks, either through focusing on the node features or the graph structure itself, it isn't always clear what the best course of action is to take. Furthermore, a lot of common explanation methods such as vanilla gradient attribution or GradCam have been shown to extract task-agnostic features in the computer vision domain, making it unclear if they're even valuable for graph neural networks. This leads us to take a step back and consider instead how one might actually train a model such that it is more amenable to post hoc explanations rather than simply using more complex post hoc explainers. To solve this problem, we leverage adversarial training as a way to mitigate non-robust feature extraction with the belief that this can help simpler post-hoc explainers key in on more interesting domain insights. To minimize overhead during training, we utilize projected gradient descent with an L-infinity norm, otherwise known as the fast gradient sign method or FGSM, and we use this to produce perturbations of the node features. To provide a little bit of background on the training of graph neural networks, the learning and feature extraction stage is facilitated through a message passing framework where node features are updated based on the other nodes within their local neighborhood. We take advantage of this to also indirectly perturb the graph structure by perturbing latent node features with our FGSM attack, with the idea that these latent node features will summarize the neighborhood. By doing this, we get away from needing to perform complicated combinatorial searches to generate adversarial attacks on the graph structure, while also removing the need to have to consider chemical constraints such as valency, which dictates how atoms can be connected to one another. Our final loss function that we use for training ends up summing the standard predictive loss that you get from the task that you're trying to solve, and the adversarial loss coming from either attacking the original node features or the latent node features. In order to test this new training paradigm in the context of explainability, we focus on a problem of interest to Lawrence Livermore, which is to identify energetic materials based on their chemical structure. This has many broad security implications, as a lot of energetic materials can end up appearing similar to what we would consider safe materials, such as pharmaceutics. And as such, to accomplish this, we curate a data set of known energetics and pharmaceutics and train a model to differentiate these molecules. Our experiments utilize a graph convolution network, which is one of the most commonly used graph neural network architectures, and we use this to solve this binary classification task. After achieving our baseline predictive accuracy, which is roughly 98 to 99% accuracy for the task, we train a set of models with adversarial training, where the adversarial attack is either on the node or latent node features, um, and we receive accuracy for those models. It is worth noting that on the adversarial training, there seems to be no substantial impact on test performance, meaning any actual improvements that we obtain on the explainability side come solely at the cost of compute time of actually calculating these attacks, which for FGSM is relatively cheap. And so now once we have these trained models, we focus on comparing the explanation capabilities of the different training setups. One obvious problem that makes explainability research difficult is simply access to labeled data. For us, while we have a lot of domain experts that can weigh in on whether an explanation makes sense given their chemical intuition, this can be hard to translate into rules that we can actually use to assess the explanation systematically. And due to this, we wanted to try to build a quantitative assessment based solely on the data and the explanations themselves. One way we do this is we leverage some previous proposed sanity checks works that were used for CNNs, which look at the correlation between explanations of a trained and randomized model and determine how the correlation changes with different experimental setups. What we find is that on average, adversarial training on the node features was able to decrease correlation between the trained and randomized model by 18% for the vanilla gradient attribution, arguing that the vanilla gradient method with adversarial training was able to more reliably extract the model's learned features and not simply rely on task agnostic features. Interestingly, methods such as GradCam on average failed to experience any significant improvements based on correlation and performed worse compared to the vanilla gradient with adversarial training, despite the more complex nature of the method, arguing that these simpler methods can work if you have the proper training set up. And to follow this up, since it may not be necessarily true that lower correlation is indicative of better feature extraction for your specific task, we also performed a blind study where we asked our domain experts to choose explanations which best reflect their domain knowledge. And what we found is that when they were presented with each of the 4 possible explanations, one for each combination of training and explanation type, the vanilla grad with adversarial training was chosen as the best explanation 84% of the time, given the explanation's compactness within the molecule and the domain relevancy of considering the specific functional groups that it denoted as important. Interestingly, when we look at the latent perturbation variation of adversarial training, we found that there was no substantial improvement to the explanation performance over the non-adversarial case. One hypothesis was that since we were explaining the nodes of the graph through the GradCam and vanilla gradient method, the adversarial training that specifically attacked the node features themselves provided the largest benefit. We looked into this a little bit further by analyzing a Bitcoin transaction data set where we used mask optimization through GNN explainer to specifically focus on the graph structure rather than nodes. But unfortunately, even with the latent perturbations here, the explanations of the adversarially trained models were only marginally better compared to the baseline. That said, given that these latent perturbations only indirectly perturb the graph structure, it may be that this method was simply ineffective and more complex structural adversarial attacks are required. And in the future, we hope to follow this work up by actually digging into some of these more complex methods and look at the relationship between the chosen adversarial attack that someone might use and the explanation method and how those can be combined to extract better insights of your models. And with that, I thank you for your time.